Alright, let's get to using this stuff. We left off with having gotten to why we have the law of cosines looking the way they do. A slightly modified, slightly scarier version of the Pythagorean theorem, but works in general. And now let's just do it. Let's just get to using it, see how it works. And as you might imagine, there is less of the trigonometry side being applied here, right? We just have one trigonometric ratio at play here, and a whole lot of algebra. And that's how it's going to work out whenever we use the law of cosines. Let me show you what I mean. Just like the law of sines, there's a best case, there's a worst case, and there's just a bit of bad news along the way. But we'll start with the best case. Where does the law of cosines work best? Well, it works best when the law of sines doesn't work at all. Right? The law of sines would not help us if we don't know any angles. But if we know no angles, we're still okay with the law of cosines. So here I have a triangle, one of the scariest triangles, according to 6, because 7, 8, 9, I'm not sorry, right? A is 7, B is 8, C is 9, and I want us to find all the interior angles of this triangle. Well, the way you can do that is you can pick any angle you want to start with, right? We need angle A, angle B, and angle C. So we just pick one of these equations. See, we need A here, and we have everything else, so we could use this first equation to find A. We don't know B, but we have all the sides, so we can use this equation to find B, and likewise for C. So we just pick any equation we want, and just go to town on it. Just see what we get, right? 7 goes over here, right? That was the A squared, and then I have B squared plus C squared minus 2BC cosine A. Cosine A, or A specifically, is the only thing I don't know. So let's see, I square this out to get 49, I square that out to get 64, and then 81 here. I subtract all that over, so I got some number on the left. I divide that by this number here, and so I end up with cosine of A is equal to some number. I then take the arc cosine of that, and I get my angle. And unlike the law of sines, this is the only thing that works, because arc cosine will give you only one value between 0 and 180 degrees. In other words, there is exactly one value, there's exactly one angle that will satisfy this equation. Or each of them, really. There will never be, in the context of angles, an ambiguous case, because arc cosine will only give you the one and only value that would satisfy the equations. So we do that for A. We're not out of the woods yet. We have to do it again for either B or for C. Not for both, right? Because once we do it for the second angle, we get the third for free just by subtracting all that out of 180. So having found B to be 58.4 degrees, so having done by having B squared equaling C squared, A squared, C squared, 2AC cosine B. So we get all the numbers off to one side, we divide by this coefficient in front of cosine, we take the arc cosine of that, and we get 58.4 degrees. So a lot of algebra. Not a lot of trigonometry, a lot of algebra though. All of the trig takes place at the very, very end, where you say, okay, whatever number I've got, let's take the arc cosine of that. That's all the trig when it comes to the law of cosines. Or is it? Yes. But there's another case. There's a second case that the law of sines fails to work with. And again, unfortunately, it's going to be very heavy on the algebra, but fairly light on the trig. So I have another case, another one that the law of sines would not have been able to help us with, because I would know side A, side B, and angle C, meaning I have no ratio of A to A or B to B or C to C that I fully realize. So the law of sines would fail me, but I can use this to find the missing side, and then go to that to find the missing angles. So let's see here. I have, A, B, and angle C. So could I use this one? No. Because I have two of the sides, but I don't have A, and I don't have the remaining sides. So this equation, such as it is with what we know, has two unknowns. Can't use it. Next one. I don't know B, and I don't know one of the sides. Two unknowns here too. This one. I do know C, and I do know A and B. So the only unknown for this equation is C. I can use this equation to find C. So let's do that. C squared being, as before, A squared plus B squared minus 2AB cosine C. I substitute all my given information in there. In goes A, in goes B, in goes angle C. So I have C squared equaling all this mess. Well, let's solve for C. Algebra tells me we take the square root of both sides. Of course, algebra would also tell us that we make it be plus or minus square root, but in this context, we don't really need to worry about the negative root, and that's because distance is always positive. C is going to be 2.95, give or take. So we now have angle C and side C. We do now have the option, in order to find the remaining angles, the law of sines. We could use the law of sines to find our remaining angles. Should we? Debatable, right? With the law of sines, you do have to consider the ambiguous case, because you could have theta and also 180 degrees minus theta, each satisfying the law of sines. And with this particular case, with the side angled side case, it's going to be exactly one solution. And so you have to do the ambiguous case and then decide which is the correct answer and which is the impossible construction, etc., and so on. Or you could just do the law of cosines again and avoid that issue entirely. Because now that I know all three sides, I can just use either of these two equations, either this one to find A, angle A, or this one to find angle B. And again, with the law of cosines, we don't have that issue arise when we take the arc cosine. So in doing that, we avoid the ambiguity entirely and say, oh, A has got to be 28.7 degrees, and B has to be about 106.3 degrees. So this is a little more writing, it's a little more computations, but there's less trigonometry, there's less ambiguity, it's more direct. So whichever works better for you at that point, go for it. But that said, I do not want to oversell you on the beauty of the law of cosines. Right? I don't want to pretend that one is better than the other. Because while the law of cosines handles this case, the side, whereas the law of sines could not, whereas the law of cosines can handle the side angle side case, whereas the law of sines could not. The other case, right, the angle side angle, right, where we have two angles in one side, it's actually impossible to use the law of cosines. You have to use the law of sines. Luckily for us, at least, that's what the law of sines is good at. That's what it does the most efficiently with no ambiguity and no issues. But if you were to look at the equations we have for the law of cosines again, you see that we have three sides and one angle in every single equation. So if you only know one side and two angles, you can't use any of these equations. You have to use the law of sines. And if you want to take a second to crack this and see what the missing dimensions are using the law of sines, I say go for it. Pause the video, pull out your calculator, do your law of sines to find the remaining pieces. The angle C, the unknown angle, you should get pretty much immediately to be 108 degrees, and then you can go from there. But for the rest of us, let's close this video out. Because we've had the best of news, we had the worst of news. Now it's time just for the bad news. And that bad news is we cannot and should not pretend that the law of cosines will somehow magically eliminate the ambiguous case. What will happen, though, is it will turn it away from a trigonometry issue, right, with the sine of the supplement being equal to the sine of the angle. That was a trigonometry issue. With the law of cosines, it becomes an algebra issue. So here's the same one we had in the previous video. Angle C was 33 degrees, B was 10, C was 6. And suppose we want to pretend that the law of cosines will make this magically better. That there is actually one solution and the law of sines is just so inept that it can't actually figure it out. So I have two known sides, one known angle. I am able to use this equation because I have my known angle and two known sides in there. I know C, and I know B, and I know angle C. So I substitute all that mess in. I've got now 6 squared is equal to my unknown side A plus 10 squared minus 2A 10 cosine 33 degrees. And I do some basic computations here. I run through this to my calculator. 36 is the square of 6. 100 is the square of 10. And all this mess will become about 16.77 and some change. I write out some additional significant figures just so I will not run the risk of rounding error, or at least to curtail the risk of rounding error. And then you'll notice, though, that what I have now is a quadratic for unknown A. I have to use the quadratic formula to find A. So it's negative b plus minus b squared minus 4ac all over 2a. So that's what it's going to have to be. And I run that through my calculator. I find that this argument reduces down to be 24.3. Take the square root of that, it's about 4.9. And if I were to subtract all that, or add all that from 16.7 and divide by 2, I get about 5.9 or 10.8, depending on if I added or if I had subtracted. So we don't avoid the ambiguous case here. It actually arises via the quadratic formula. It's an algebra issue. So there's no brute force way to handle the ambiguous case. You either have to be smart with your quadratic evaluating skills, with your quadratic formula, or you have to be smart with your trigonometry skills when you're dealing with the arc sine. In either case, you just have to be smart with it. And we will do some examples of this in class, as well as the more basic, straightforward, non-ambiguous cases. And that, between that and what you're seeing now and what you'll do at your own time outside of class, hopefully that will bring everything into light. If not, do let me know. And go ahead and let me know right now what issue you feel you're having the most, or what you will have the most. So do that for me, and I will see you up ahead.